are important to us because we want to find the total area for these rectangles. So let's go ahead and write down our results. So the total area is going to equal the following. Remember, area of a rectangle, you got to take the base times the height. So for this first rectangle, the base value is 100 times its height is 0. The height is just going to be the y coordinate of that point. So I've got to take a 100 times 0. For the second rectangle, that's going to still have the same base value of 100 times its height, which is 50,000. For the third rectangle, the base is still 100. Then I've got to multiply by its height. That's 80,000. So we're just going to go down the list here. So the fourth one is 100 times 90,000. The fifth one is 100 times 80,000. And the last one is 100 times 50,000. And then we need to add all of those areas together to get our total. And we'll go ahead and I'll show you this. Of course, the first one is just 0, so I'm not going to bother with that one. The second one is just 50,000 times 100. Another thing I'll show you, kind of a little shortcut. Since you're always going to be multiplying by the same amount here, what you could do instead of typing these in individually is you could just take 100 and then open a set of parentheses and then run down your y values, your heights. So I'll go ahead and type in the 0 even though it's not necessary. But if I put 0 plus 50,000 plus the 80,000 plus the 90,000 plus the 80,000 plus the 50,000. And when I hit enter, I'm getting that total of 35 million for the total area. So let's go ahead and jot that down. Now let's talk about the important takeaways. First of all, remember what this process is for. If you have a function that is given and you find the area under that function, that area is going to correspond to the value of the antiderivative of that graph. So whatever this graph represents is the derivative of something. By finding the area under that graph, we're evaluating the antiderivative. We're figuring out the value of the antiderivative. Now, to do that when the area is nice and simple, like on the first couple of examples, we can use basic geometry. If that's not possible, we're approximating the total area using this Riemann summation. Now, of course, one takeaway from this, we know that this 35 million would not be equal to the exact area, but this is an approximation. Now, of course, and here's one final thought here before we wrap it up. The more rectangles that you use, the more accurate this approximation would be. So think about what's happening here. We used a total of 6 rectangles. If we had used 12 rectangles, right? If we had used twice as many, this empty space and this overhang would be smaller in total than what we're seeing here. Next, imagine what if we were to use not 6 rectangles or 12 rectangles, but 100 of these things? Or why not 1,000 or 1,000,000? By increasing the number of rectangles, you're going to make this approximation more and more accurate. And of course, and maybe you can see where this is all going, if we were to use infinitely many rectangles under this curve, then the approximated area would end up equaling the exact area that we're after. And of course, we know a process that would allow the number of rectangles to approach infinity. That's what calculus is. It's that limit process. And that's where we're going to see this idea continued over into our next section. For now, If you're having any trouble with section 4.2, make sure to go back, relook at the examples, rework them, try the problems on MyMathLab, and if you're having problems, just let me know. I'd be glad to help you. All for now.